Usually when we talk about structural engineering, um, there's this expectation of absolute, pristine precision. Downward force meets upward
Oh,
resistance.
yeah, totally static.
Right. Gravity just pulls a slab down, columns transfer that load directly to the foundation, and the blueprint basically just points and says, that holds that.
Yeah, it's a very reliable universe where buildings are supposed to just sit there and behave themselves.
But the second you step into the world of seismic engineering, that entire static framework just completely shatters.
It absolutely shatters. I mean, you transition from a world of predictable, constant gravity into this completely dynamic, chaotic landscape.
Which is terrifying, honestly.
It is. Designing a building to survive an earthquake is, well, it's the ultimate exercise in engineering for the unpredictable.
So, welcome to this custom-tailored deep dive. Our mission today for you, the listener, is to completely demystify seismic engineering, and specifically, the ASCE 722 seismic design criteria.
Which is a very hefty code book.
Oh, it's massive. But if you've ever looked at a towering skyscraper or, even just the local hospital down the street and wondered how someone actually calculates the math to ensure it doesn't collapse when the Earth itself violently gives way, well, you are in the right place.
We are going to translate all of it.
Exactly. We're taking this incredibly dense engineering code, a document that, frankly, looks like an impenetrable alphabet soup of variables like S's, R, SDC, and CVX, and we're turning it into a clear, logical journey.
And to start that journey, we really have to completely discard how we intuitively think about forces acting on a structure.
Because it's not like wind.
Right, not at all. When you design for wind, the mechanics are obvious. The wind physically pushes against the exterior glass and the walls of the building. But an earthquake doesn't push a building at all.
It just moves the ground underneath the foundation.
Precisely. The code relies entirely on inertial mass.
So if you are sitting in a building right now, just look up at the ceiling, look at the concrete floor slabs. During an earthquake, those heavy static elements basically become the weapon.
Yeah, the earthquake doesn't hit the building hits itself.
I love that phrase. It hits itself.
It's the perfect way to visualize it. Because seismic force is an inertial force. Imagine you are standing on the subway train, right? And you're not holding the handrail.
Always a bad idea.
Always. But when the train accelerates forward out of the station, you are thrown backward. But the train didn't push your chest backward, it pulled your feet forward.
And the mass of your upper body simply wanted to remain exactly where it was.
Exactly. Inertia. So in a building, the floor slabs act like your upper body. They hold the vast majority of the structure's mass.
Right, mostly in the concrete.
Yeah. So when the ground violently accelerates laterally, that immense mass resists the movement. The more massive the building and the more violent the ground acceleration, well, the greater the lateral force trying to just shear the structure apart.
So we're dealing with a dynamic system, not just a block of concrete sitting on the dirt. The code actually uses the analogy of a spring mass system, right?
It does, yeah.
A building is basically a heavy weight sitting on top of a stiff spring. And because it's on a spring, it sways. Which brings us to our first major fundamental concept today, which is the period of vibration.
Right, so every single object in the physical universe has a natural period of vibration.
Like a guitar string.
Sure, like a guitar string. In seismic engineering, the period, which we denote with the letter T, is the exact time it takes for a building to sway all the way to one side, swing completely back to the opposite side, and then return to its original center position.
And we measure that in seconds.
Yes, exactly, in seconds.
But earthquakes aren't just one monolithic shove, right? They produce seismic waves that also have specific periods.
Very true. You have short period waves, which are characterized by incredibly high ground acceleration. Think of a very rapid, violent, just back and forth jerking motion.
Really aggressive shaking.
Yeah. And then you have long period waves. These are characterized more by ground velocity and displacement. The ground is actually traveling further distances, moving back and forth much more slowly.
And the frequency of those waves interacts directly with the stiffness of the structure they hit.
Exactly. So short period, high acceleration waves, those dictate the design of short, stiff buildings.
Like a one-story wood-framed house.
Or a rigid masonry block building. They have a short natural period, so they feel those rapid jerks intensely. Conversely, long period waves dictate the design of tall, flexible buildings like a 40-story skyscraper.
Because a skyscraper has a very long natural period. It wants to sway slowly.
You got it.
Let me throw an analogy at this. Imagine you have a workbench, and on it you have a rigid little coffee mug, and right next to it a tall, flexible metronome, or like a tuning fork.
Okay, I can picture that.
If you take a hammer and rapidly bang on the side of the workbench, which is our short-period high-acceleration wave, the coffee mug chatters violently and tips over.
Right, but the tall metronome barely registers the rapid vibration.
Exactly. But if you grab the workbench and slowly, rhythmically shove it back and forth, our long-period wave, the coffee mug just rides along safely. But the metronome starts swaying wildly in time with your pushes until it snaps.
Wow, yeah. What you are describing there is the phenomenon of resonance. And honestly, it is the single most terrifying word in structural dynamics.
Resonance.
Yeah. Resonance occurs when the period of the earthquake's wave perfectly matches the building's natural period of vibration.
So if a short, choppy wave hits a short, stiff building, or a slow, rolling wave hits a tall skyscraper,
The shaking is amplified exponentially. Each wave pushes the building exactly as it naturally wants to sway, injecting more and more energy into the system.
it's just like pushing a child on a playground swing at the precise peak of their arc.
Yes, exactly. The displacement just grows and grows until the structure literally tears itself apart.
Which means knowing how our specific building sways is only half the equation. To calculate the actual force it's going to experience, we have to know exactly where this building is sitting and what purpose it serves in society.
Right, the context of the building is everything.
So let's look at how ASCE 722 forces engineers to categorize a project before any math even happens. Let's start with risk categories.
Okay, so the code demands that we evaluate the consequence of a structural failure. There are 4 risk categories, ranging from I to I phi, and it fundamentally changes the design baseline.
Let's contextualize this for the listener. Imagine a coastal town. Out on the edge of town, you have a massive agricultural barn storing tractors and fertilizer. That is risk category 1.
Right, risk category 1.
If a massive earthquake hits and that barn collapses, I mean, it's a significant financial loss for the farmer, but the risk to human life is incredibly low. There just aren't people inside.
But move into the center of that town. You have standard houses, office buildings, maybe a local retail store. Those are all risk category 2.
So risk category 2 is basically the default.
Yes, it's the baseline default for the vast majority of structures. If they fail, lives are absolutely at risk, so the safety standards are very stringent.
Then we step up to category 3. This is where the density of human life really spikes.
Right. We are talking about the town's high school, a massive movie theater, or a crowded auditorium.
Because if a category 2 office building falls, it's tragic. But if a category 3 auditorium with 1,000 people inside falls during a performance,
It is an unparalleled catastrophe. The code recognizes that dense concentration of human life.
and finally you reach risk category 3, which represents essential facilities.
The town's hospital, the 911 dispatch center, the fire station.
The ones that have to survive.
Exactly. The code explicitly dictates that these buildings do not just need to protect the people inside them during the shaking. They must remain entirely operational the second the shaking stops.
Because the monitors in the emergency room still need power.
And the structural frame must be intact enough to safely triage victims pulled from the rubble of all the other buildings.
All right, so an engineer designing the hospital and an engineer designing the barn are playing by completely different rules, even if they're building on the exact same street.
Entirely different rules.
But the street itself, the actual dirt they're building on, is the next massive variable. We have to determine the site class.
Site class is a categorization of the soil's stiffness, and it ranges from A to F.
And how do they figure that out?
It is typically determined by a geotechnical engineer measuring the shear wave velocity.
Which is literally how fast a seismic wave travels through the top 100 feet of the earth.
You got it. So
That's it.
site class A and B represent hard, solid rock. This is highly favorable.
Makes sense.
Then site class D is stiff soil, which ASCE E7 actually mandates as the default assumption if you haven't done specific geological testing.
Okay, so D is the middle ground.
Yeah. But then you drop down to site class E and F. These are soft clays, loose sands, swampy fills, highly unfavorable.
Now, I want to push back on that intuition a little bit.
Go for it.
Because if I'm picturing an earthquake, I might assume that building on solid, rigid rock would mean my building takes the absolute hardest, most violent hit possible. Wouldn't a deep bed of soft clay act like a shock absorber? Shouldn't it cushion the blow?
That is a very common misconception, and sadly, that assumption has historically cost thousands of lives.
Wow.
Yeah. To understand the catastrophic danger of soft soil, we have to examine the 1985 Mexico City earthquake.
Okay, let's talk about Mexico City.
So Mexico City is built on the drained bed of an ancient lake. It is essentially a deep, bowl-like basin filled with soft, jelly-like clay.
Textbook cite Class E and F soil.
Exactly. And the earthquake itself didn't even happen in the city.
Right, the epicenter was off the Pacific coast, like hundreds of miles away.
Yeah, so by the time the seismic waves traveled through the Earth's crust and reached the rocky mountainous areas surrounding Mexico City, a lot of the high-frequency energy had dissipated.
The waves hitting the rock were actually quite weak by the time they got there.
Very weak. If the city had been built on rock, it likely would have been a pretty minor event.
But the waves didn't stay in the rock. They hit that ancient lake bed.
Right. And when those weak, distant seismic waves transitioned from the hard rock into that deep basin of soft clay, the soil did not cushion them at all. It acted as a massive amplifier.
Because soft soils trap the seismic energy.
Yes. They slow the waves down but dramatically increase their amplitude, which is the height of the wave. It took a distant, moderate shape and magnified it into a localized, violent, long-period rolling motion.
And this ties right back to resonance.
Deeply. The amplified waves passing through that soft clay developed a very specific long period of around 2 seconds.
And that matched the buildings.
Perfectly. Because of resonance, those specific waves perfectly matched the natural sway of buildings that were about 6 to 15 stories tall.
Oh man, so the mid-rises.
Yeah. Those mid-rise buildings acted exactly like the metronome on our workbench. They absorbed massive amounts of energy, swaying wider and wider until hundreds of them suffered catastrophic pancaking collapse.
That's horrifying. But the short buildings and the really tall ones were fine.
Mostly, yes. Short, stiff buildings and massive 40-story skyscrapers right next door survived with minimal damage because their periods didn't match the amplified soil. So the lesson is, soft soil is an amplifier, never a cushion.
That is a staggering realization.
Yeah.
So we have our soil type ready to act as a potential amplifier and our risk category defining our human stakes.
We have the baseline.
Now, how does the ASCE 722 code actually force us to calculate the earthquake? How do we turn raw geological data into engineering math?
That's where we get into the variables.
Let's trace the journey of an earthquake wave, starting from the bedrock up through the soil into the code book.
Well, everything begins with the United States Geological Survey, the USGS. They maintain a massive, incredibly detailed seismic design geodatabase.
Right.
An engineer types in the exact GPS coordinates of their site, and the database spits out 2 raw foundational values, S's and S1.
Let's dissect those. What exactly are S's and S1?
The S stands for spectral response acceleration. It is a measure of how hard the ground is accelerating.
And the little s?
The little s in S's stands for a short period, specifically a 0.2-second wave.
Okay, and S1?
The 1 in S1 stands for a 1-second period, representing our long, rolling waves. Now, these are not just average earthquakes. These numbers represent the mapped acceleration at bedrock for a maximum considered earthquake, or MCE.
The MCE is the absolute worst-case scenario, correct? The big one.
The big one.
The code defines it statistically as an earthquake that has only a 2% probability of being exceeded in a 50-year period. It is a massive generational seismic event.
Exactly. So S's and S1 represent how violently the bare bedrock will shake during that rare, massive event.
But as we just established with Mexico City, very few buildings sit directly on bare bedrock.
Right. We have to adjust those raw mapped values for the specific dirt at our site. We do this by multiplying our raw S's and S1 by site coefficients, which are known as Φ and Fi.
So Φ acts on the short period acceleration, adjusting it based on the soil, and Fv acts on the velocity-driven 1-second period acceleration.
You've got it.
So we take our map bedrock S's, multiply by Φ to account for our soil amplification, and we arrive at SIMS.
Yes.
And we take our mapped S1, multiply it by Fv, and we get SM1. The M still stands for MCE, right?
It does. SIMS and SM1 are our site-adjusted maximum considered earthquake parameters. They tell us exactly how violently the surface of the ground at our specific site, modified by our specific soil, will accelerate during the biggest earthquake statistically imaginable.
Okay, I'm with you. But this is where ASCE 722 introduces a fascinating and honestly slightly terrifying pivot.
Oh, the 2/3 rule.
Yeah. We don't actually design the building to withstand SIMS and SM1. The code dictates that we multiply those values by 2/3.
That's right. We intentionally reduce the worst-case scenario forces by 33.3%.
So when we multiply SIMS by 2/3, we get SIMSs. And when we multiply SM1 by 2/3, we get ST1.
And the D stands for design. SDs and SD1 are the actual design spectral acceleration parameters that an engineer will use for every single calculation from this point forward.
I have to stop you there. Why on earth would the engineering code intentionally mandate that we design a building for a weaker earthquake than the geological data explicitly says is possible? That sounds like a massive liability.
I know it sounds crazy, but it's entirely about societal economics and the philosophy of acceptable risk.
Okay, explain that.
If the code demanded that every single office building, apartment complex, and retail store be built practically invincible,
Right.
designed to remain perfectly pristine and undamaged during an MCE, the sheer volume of steel, concrete, and labor required would be astronomical.
It would just be too expensive.
It would be economically impossible to build anything. Construction would grind to a halt.
So the two-thirds reduction is a compromise.
It is a highly calculated balance between safety and economics. We designed for what is called the design basis earthquake.
The DBE.
Right. The underlying philosophy of ASCE 722 is not property preservation, it is life safety.
Oh, yeah.
The code assumes that if the full 100% maximum considered earthquake actually hits, a building designed to the two-thirds level will suffer severe, unrepairable structural damage.
The drywall will shatter, the frame will permanently warp.
Exactly. The building will likely be condemned as a total economic loss. But, and this is the absolute core of the code, it will not collapse.
It will remain standing just long enough for every human being inside to evacuate.
Yes. We are sacrificing the building to save the people.
Okay, that clarifies so much. It's a language of survival, not invincibility. So now that we have SDs and SD1 are finalized, soil amplified, economically reduced, ground-shaking numbers, the code uses them to assign the building a specific legally binding rulebook.
That rulebook is the Seismic Design Category, or SDC.
And it is assigned as a letter grade, right? From A through F.
Correct. It is derived by cross-referencing the building's risk category with its SDs and SD1 values. It essentially asks the matrix, how violent is the expected shaking and how catastrophic would it be if this specific building fell?
Right. Seismic Design Category A is the lowest tier. You might see this for a standard warehouse in Florida, where seismic activity is practically zero.
The requirements are very minimal there. You're mostly just ensuring the roof is tied down to the walls properly.
But as you move into SDCD, E and F, which dominate high seismic zones like California, Alaska, and the Pacific Northwest, the requirements escalate exponentially.
They really do. And it is vital to understand that SDC isn't just a multiplier that makes the math heavier. It is a binary switch. It is a massive list of thou shalt nots.
Give me an example of that. How does SDC act as a switch?
Well, if a building is assigned to SDCD or higher, certain structural materials and systems are completely outlawed. For instance, you cannot use ordinary plain concrete shear walls. The code looks at the violent shaking anticipated in SDCD and says, plain concrete is far too brittle. It will shatter. You are legally required to use special reinforced concrete with intense, highly ductile steel detailing.
Oh, wow.
It also triggers mandatory requirements for independent peer reviews, specialized structural observations during construction, and rigorous material testing. SDC literally strips away certain tools from the engineer's toolbox to prevent catastrophic brittle failures.
Got it. And alongside the SDC, we have to apply the seismic importance factor, denoted as IE. This ties right back to the risk categories we discussed earlier.
Exactly. A standard office building, risk category 2, has an importance factor of 1.0. It doesn't change the math.
But our hospital, our risk category 4th essential facility, gets an importance factor of 1.5.
Yes. Which means we are effectively taking every single earthquake force calculated for that hospital and multiplying it by 1.5.
Requiring it to be 50% stronger than the office building right next door, simply because of its societal purpose.
Exactly, because we cannot accept the hospital becoming a total economic loss that requires evacuation. We need the lights on and the surgeons operating.
Okay, so we know our building's rulebook and we know our design acceleration. Now we have to pick the actual physical skeleton that will resist these forces.
The structural system.
Right. And this introduces the most fascinating paradox in structural engineering. To survive a massive force, we actually design the building to be weak in very specific, highly controlled ways. Let's talk about the system factors.
Oh, the secret weapons. When an engineer selects a seismic force resisting system, whether that's a concrete shear wall, a timber frame, or a steel moment frame, they must pull 3 critical parameters from table 12.2 to 1 in ASCE 7.
And these parameters define how the building skeleton will deform under stress.
Yes. The most impactful and often the most confusing is the response modification coefficient, or the R factor.
The R factor is a massive mathematical reduction. Depending on the system, an R value might be 5, 6.5, or even 8.
Yeah, up to 8.
And in the equations, R is in the denominator. We are literally dividing the destructive force of the earthquake by 8. Why are we legally allowed to pretend the earthquake is 8 times weaker than it is?
Because of the physics of ductility. Ductility is a material's ability to yield, warp, bend, and permanently deform without actually fracturing or losing its capacity to carry gravity loads.
Think of the crystalline structure of steel. You can bend a steel paperclip back and forth.
Exactly.
The metal physically deforms. It yields. The molecular bonds stretch and slip, turning kinetic energy into heat, but it doesn't immediately snap in half.
That permanent deformation is the key. When a steel beam in a building yields during an earthquake, that distortion acts as a massive energy sec. It absorbs a tremendous amount of the earthquake's kinetic energy.
So if it didn't yield,
If we attempted to build a structure to remain perfectly elastic, meaning it flexes during the earthquake and snaps back perfectly to its original shape with zero permanent damage, it would have to be incredibly, impossibly massive. The walls would be solid steel.
that's just not practical.
No. By utilizing a high ductility system with an R factor of 8, the code accepts that the building will permanently deform. We will allow the steel to warp. And because that warping absorbs so much energy, the actual elastic force the structure needs to resist to stay standing is significantly smaller.
We are purposefully designing the building to bend so it doesn't break. But wait, if we are dividing our forces by 8 under the assumption that the steel beams are going to act as yielding fuses, well, what happens if the steel mill sends us a beam that is actually way stronger than we asked for?
That is the million-dollar question.
Because if it's too strong, it won't yield, right?
That scenario is a structural engineer's nightmare, and it is exactly why the code mandates the second parameter, the system overstrength parameter.
Denoted by the Greek letter omega sub-zero, right? Omega naught.
Yes. Steel often arrives from the mill with a yield strength far exceeding the specified minimum. You design for 50 kc steel, and the mill delivers 65 kc steel.
To a layperson, getting 15 kSi of extra strength for free sounds like a massive win.
In a static gravity environment, it is. In a seismic environment, it is lethal.
Because it messes up the fuse.
Exactly. If a beam is designed to act as our ductile fuse, but it is unexpectedly super strong, the earthquake will hit it and the beam will refuse to yield. Instead of absorbing the energy through deformation, that super strong beam will act as a rigid conduit,
Sending all the force down the line.
transferring all of that massive, unyielding seismic force directly into its connections, the bolts and welds tying it to the columns.
And connections are inherently brittle. You can't bend a weld. A weld just snaps.
Precisely. If the connection snaps, the beam drops, the column loses bracing, and the pancaking begins. So omega is an amplification multiplier, typically around 2.0 to 3.0.
Okay, so we scale it back up.
We are required to multiply our seismic forces by omega exclusively when designing critical non-ductile components like connections, collector beams, and columns.
It forces the engineer to design the connection to be astronomically stronger than the beam.
We are mathematically guaranteeing that no matter how strong the steel mill made that beam, the beam will always warp before the connection ever snaps.
We are dictating the exact location of the failure. We are telling the building exactly how it is allowed to break.
It's controlled demolition almost.
That brings us to the third parameter, CD, the deflection amplification factor. If we used our R factor to artificially shrink our design forces because we plan on the building yielding, then any calculation we do to figure out how far the building sways sideways is going to be wildly inaccurate, right?
Yes, completely. If you calculate the horizontal sway of the deflection using the R-reduced forces, the math will tell you the building barely moves.
Which is a dangerous illusion.
SEED exists to scale that deflection back up to reality. It accounts for the inelastic, permanent warping that the R factor assumes will happen.
We have to know the true scaled-up sway so we can ensure the building doesn't literally lean over and crash into the building next door.
Right, a phenomenon called seismic pounding. We also need to know how much the floors will warp so we can ensure the glass exterior windows don't shatter down onto the street.
To make these abstract system factors highly tangible, we can look at a very specific structural system detailed in ASCE E7, which is the Steel Eccentrically Braced Frame, or EBF. It is a masterpiece of manipulating R, omega, and CD.
It really is an elegant system.
Let's visualize this. A standard concentrically braced frame is something you see on construction sites all the time. It looks like a giant steel X between two columns.
Right, the diagonal braces meet perfectly in the middle.
It's incredibly stiff, which is great for wind, but it lacks ductility.
Mm.
Under the immense compression of an earthquake, those long diagonal braces tend to buckle, and buckle violently.
Right, but an eccentrically braced frame intentionally breaks that perfect geometry. The diagonal brace does not connect perfectly to the corner intersection of the beam and column.
So where does it go?
Instead, it is offset. It frames into the horizontal beam a short distance away from the column, or a short distance away from the other intersecting brace.
So it leaves a small, intentionally isolated gap, a short segment of the horizontal steel beam.
Exactly. That short isolated segment of the beam is called the link, and it is the mechanical heart of the EBF system. That link is highly engineered to act exactly like an electrical fuse in your home's breaker box.
Okay, I see where this is going.
During a minor earthquake or heavy wind, the EBF remains stiff. The link holds firm. But when a massive MCE hits, the forces skyrocket. Before the columns can buckle and before the braces can snap, that specific isolated link beam is designed to yield and shear.
Yielding and shear means the web of the steel I-beam is literally distorting, warping into a parallelogram, absorbing massive amounts of kinetic energy, while the heavy top and bottom flanges try to hold it together.
It acts as a sacrificial crumple zone. It protects the gravity columns and the braces by taking all the damage upon itself.
I love that. It is exactly like the crumple zone on the front of a car.
Yes, perfect analogy.
The engineers want the hood of the car to crush and fold like an accordion so that the passenger cabin remains completely intact. In a building, the link beam crushes and yields, so the gravity columns, the passenger cabin of the building, stay standing.
And after the earthquake, theoretically, you could prop up the floor, cut out that yielded, mangled link beam with a torch, and weld in a brand new one while the rest of the building's skeleton is unharmed.
That controlled sacrifice is why an EBF is granted a very high R factor, often around 8.
Exactly.
Okay, so we have our soil-adjusted acceleration from the USGS, which is SDS. We have our ductility reduction factor, R. And we have our importance factor, i.e.
We have all the pieces.
We are finally ready to calculate the total physical force of the earthquake hitting the building. This is the realm of the equivalent lateral force procedure, or ELF, and the calculation of base shear.
ASCE 7 provides engineers with several analytical paths. There is modal response spectrum analysis and nonlinear response history analysis,
Which sound very intense.
They are highly complex, computationally heavy simulations. They use 3D models to literally simulate specific earthquake wave records passing through a structure millisecond by millisecond.
But we don't use those for every building.
No, those are generally reserved for incredibly tall, twisted, or highly irregular skyscrapers. For the vast majority of standard, regular buildings, the mid-rises, the hospitals, the schools, we rely on the equivalent lateral force procedure, the ELF.
The absolute workhorse of the structural engineering industry.
The genius of the ELF procedure is its simplicity. It takes the chaotic, dynamic, oscillating ground shaking of an earthquake and simplifies it into a set of static horizontal arrows pushing against the side of the building at each floor.
But before we can figure out how hard to push on each floor, we have to find the total sum of that pushing force at the very bottom of the building. This is called the seismic base shear, denoted by the letter V.
Right, and the formula for base shear is elegantly simple. V equals C is multiplied by W.
Base shear equals the seismic response coefficient, C's times the effective seismic weight of the building, W.
Let's dig into W, the weight, because calculating what actually counts as weight during an earthquake is incredibly counterintuitive.
We aren't just putting the building on a scale.
No, we are calculating the effective seismic weight, the mass that is rigidly attached enough to generate an inertial force when the ground moves. First, obviously, 100% of the dead load is included.
The steel frame, the concrete slabs, the permanent walls, the roof materials. That mass is permanent and rigid. But what about the live load? You know, the humans, the desks, the rolling office chairs.
In a lot of minds, a building packed with 1,000 people weighs more, so it should generate more force.
That's what I would assume.
It weighs more under gravity, yes.
Nah.
But live load is generally not included in the effective seismic weight.
Wait, really? Humans don't count.
Walking humans, rolling chairs, and loose furniture do not move in perfect, rigid unison with the building's structural frame during a violent shaking event. They slide around, they bounce, they lose their footing.
Oh. Because they are not rigidly attached, their mass does not contribute purely to the building's inertial force.
Exactly.
But there are exceptions to that rule in the code, right? What if the live load isn't a person, but a tightly packed warehouse?
That's the exception. If a floor is designated for storage, ASCE 7 mandates we include 25% of that storage live load in the seismic weight. A warehouse floor stacked to the ceiling with heavy pallets of books packed tightly together will absolutely move with the building.
That makes sense.
We also must include a flat 10 pounds per square foot allowance for interior partition walls because even though they aren't structural, they are physically screwed to the floors.
And then there's the variable of weather, snow.
Snow is a critical inertial mass. If the flat roof snow load in a region exceeds 30 pounds per square foot, meaning a heavy, dense accumulation of snow or solid ice, you must include a percentage of it, typically 20%, in the effective seismic weight.
Because a foot of solid ice blanketing a massive warehouse roof acts as a huge, heavy slab of inertia sitting at the absolute highest point of the building, maximizing its destructive leverage. So V equals C's times W. The base shear, V, is essentially the giant invisible hand of the earthquake grabbing the building right at the foundation, trying to shear its ankles off.
Great visual.
To calculate the power of that invisible hand, we multiply the entire effective weight of the building, W, by our seismic coefficient, C's. But where does C's come from?
The base equation for C's is found in ASCE 7, section 12.8.1.1. It synthesizes everything we've talked about so far.
Okay, let's hear the math.
The equation is CS equals SDS divided by the quantity R divided by I.
Let's translate that math into a narrative for the listener. It takes the design ground acceleration dictated by the USGS and our soil, which is STS. It reduces that acceleration heavily based on the structural system's ability to warp and yield, which is the R factor.
Right.
And it bumps it back up slightly based on how critical the building is to society, the importance factor, i.e.
That is the starting point. But the code provides a series of upper limits, or caps, on C's, and these caps are entirely dependent on the building's fundamental period, T.
Why do we need caps?
Well, if a building is incredibly stiff, say, a short masonry block building, it has a very short period. The raw math of that base equation might spit out an astronomically high C's value, requiring an absurd amount of structural steel.
Which would be too expensive again.
Right. The code caps it so you don't over-design to an economically crippling degree based on empirical testing of how stiff structures actually respond. Conversely, if the building is highly flexible, with a long period, it enters a completely different part of the seismic response spectrum.
Because the acceleration matters less and the velocity of the ground wave matters more.
Yes. So for a tall, long-period building, the C's equation changes.
In that long period realm, the cap equation utilizes SD1, our 1 second period mapped parameter divided by the period T, modified again by R and IE.
Exactly.
Which means we absolutely cannot calculate our base shear without knowing the exact period T of the building. But here's the paradox.
Yeah.
How does an engineer know exactly how many seconds it takes for a building to sway back and forth before they've even built it or even sized the beams?
They don't. They have to use an estimation called the approximate fundamental period, denoted as Ta.
And there's a formula for that.
ASCE 7 provides an empirical formula derived from decades of measuring real buildings during earthquakes. The formula is Ta equals CT multiplied by HN raised to the power of X.
Let's break those variables down.
HN is simply the structural height of the building in feet from the base to the roof. The parameters CT and X are coefficients you look up in a code table, and they're based entirely on the building's structural material.
So a flexible steel moment frame will have different CT and X values than a highly rigid concrete shear wall.
Correct. You plug the total height into the formula with those material parameters, and it spits out a conservative, mathematically safe estimate of the period in seconds.
You use that Ta to finalize your C's coefficient, multiply it by your building's weight W, and boom, you have your total base shear, V, measured in thousands of pounds or kips.
But having the base shear is not the end of the analysis.
Right, because a building is not just a flat plate sitting on the ground.
It has height, it has verticality, we have this massive total lateral force down at the foundation, but to actually design the beams and columns on the 4th floor or the 10th floor, we have to distribute that total force vertically up the height of the building.
This is where the ELF procedure gets incredibly clever. We have to slice that total base shear, V, into individual horizontal arrows pushing on each specific floor level. We call the force at a specific level Fx.
Right, and the formula is Fx equals CVx multiplied by V.
So the force at floor X equals a vertical distribution factor, CVX, multiplied by the total base shear.
Exactly.
How does the math determine that CVX factor? It's not just dividing the total force equally by the number of floors, right?
Absolutely not. CVX is a weighted ratio based on mass and height. To find CVX for a specific floor, say the fifth floor, you take the weight of that fifth floor, WX, and multiply it by its height from the base, HX, raised to an exponent K.
That gives you a leverage value for the fifth floor.
Then you divide that by the sum of that exact same calculation done for every single floor in the entire building.
Conceptually, you are calculating what percentage of the total weight times height leverage belongs to that specific floor. A 100,000-pound floor level at 10 feet in the air has much less leverage than a 100,000-pound floor level at 100 feet in the air.
Yes. The heavier the floor, the larger the percentage of the force it takes. The higher up the floor is, the larger the percentage of the force it takes.
Exactly, and the behavior of that distribution is controlled by the exponent K.
And K is a variable entirely dependent on the building's period T.
Let's explore K. If the period T is less than or equal to 0.5 seconds, which means we have a short, stiff building, K equals 1.
If K is 1, the math is entirely linear. Because height, h, is just raised to the power of 1, the vertical distribution of forces looks like a perfect upside-down triangle.
So the very top floor takes the largest chunk of the lateral force, and the force decreases linearly in a straight line down to the ground floor.
That's right. But if the period t is greater than or equal to 2.5 seconds, a tall, flexible building K equals 2. And this is where the math beautifully mimics reality.
Because you are squaring the height, h squared, in the equation.
The distribution is no longer a straight line. It becomes a parabola. It whips an exponentially larger share of the total base shear to the very top levels of the building.
Let me use an analogy here. Imagine balancing a heavy push broom on the palm of your hand.
Okay.
If the heavy brush head is down near your hand, it's fairly easy to balance. The mass isn't exerting much leverage. But flip that broom upside down.
Now that heavy brush is 10 feet in the air.
Exactly. The mass at the very top exerts a huge lever arm effect. Even a tiny movement of your hand at the bottom creates a violent, sweeping, whipping motion at the top.
That whip-like dynamic behavior is exactly what tall buildings experience during an earthquake. The K exponent of 2 is the ELF procedure's way of forcing the static math to replicate that dynamic whipping.
By assigning massive forces to the roof, it ensures the engineer designs the structural columns to resist the immense bending moments created by that top-heavy inertia. So we have found our base shear, and we have distributed it as horizontal forces, pushing sideways on every single floor. The frame is mapped out.
We're almost done.
But before an engineer can finalize the blueprints, the ASCE 722 code demands a series of final, highly punitive checks for redundancy and the combination of horizontal and vertical earthquake effects.
Let's start with the redundancy factor, denoted by the Greek letter rho. The code heavily penalizes structures that lack backup systems.
Because in structural engineering, redundancy is life.
It really is. If a building's survival relies entirely on just 2 massive concrete shear walls, and an unexpected flaw causes one of those walls to fail during an earthquake, the entire building loses 50% of its capacity and collapses. That system is not redundant.
So the code forces the engineer to digitally sabotage their own design. You literally go into the computer model and remove a single brace or a single shear wall.
You simulate a localized failure. If removing that one element causes the rest of the building's story strength to drop by more than 33%, or if it creates an extreme torsional twisting effect because the building is suddenly lopsided, your system fails a redundancy check.
And the penalty for failing is brutal.
Very brutal. You are assigned a redundancy factor, rho, of 1.3. This means you are legally required to scale up all of the horizontal earthquake forces you just painstakingly calculated by 30%.
Which forces the engineer to massively over-design the remaining elements to compensate for the lack of backup.
Right. However, if your shear walls and moment frames are well distributed throughout the floor plan, and removing one element doesn't cripple the structure, you are rewarded with a rho of 1.0, no penalty.
I love that mechanism. It's the code using math to mandate a good, holistic design philosophy. So we multiply our horizontal forces by our redundancy factor, and we arrive at the final effective horizontal force, denoted as A.
But we are missing half the earthquake.
Right. Earthquakes don't just shove buildings side to side. The ground also violently jumps up and drops down.
Which brings us to EV, the effective vertical force. The formula for EV is 0.2 multiplied by our design acceleration ASCE, multiplied by the dead load.
What is that 0.2 actually representing conceptually?
It represents 20% of the building's dead load acting as a vertical acceleration factor. It mimics the effect of gravity temporarily fluctuating.
Like gravity getting stronger.
Exactly. When the ground violently accelerates upward into the foundation of the building, it feels as though the dead load of the building suddenly increased. The columns suddenly have to support a massive spike in weight.
And conversely, when the ground drops out from under the building during the downward wave, it feels like the dead weight has temporarily vanished.
It is the exact sensation you feel in a fast elevator that suddenly drops. You feel light on your feet.
And understanding the terrifying interplay between the horizontal pushing and that vertical jumping, AVE, is critical for our final global structural checks at the foundation. Let's walk through what these combined forces are actually trying to do to the building globally. Let's start with overturning moment.
Okay, so the horizontal forces we distributed to each floor act as lever arms. Pushing horizontally on the roof of a 100-foot building creates immense rotational leverage at the ground level.
The earthquake is literally trying to tip the entire building over like a domino.
Yes, that rotational force is the overturning moment.
Next, we check base shear again, but at the foundation level. The lateral force is acting right at the ground line, trying to shear the building off its concrete foundation, like snapping a stick over your knee.
Then we evaluate sliding. That same lateral base shear isn't just attacking the columns, it is pushing against the concrete foundation itself, trying to physically slide the entire building sideways through the dirt.
So the engineer must ensure the friction of the soil against the concrete is enough to resist sliding.
Right. And finally, bearing.
Bearing is intimately tied to the overturning moment, isn't it?
Very intimately. As the horizontal earthquake tries to tip the building over, it lifts up on one side of the foundation and pushes down with immense concentrated pressure on the opposite edge.
It's like standing flat-footed and someone pushes your chest, forcing you to lean all your body weight entirely onto your big toe.
That's a great way to think about it. The soil directly beneath that toe, the outer edge of the foundation, must have enough bearing capacity to not crush, sink, or liquefy under that massive temporary pressure spike.
And this is why the vertical force, EV, is the silent killer. If the earthquake pushes the building sideways with maximum, generating a huge overturning moment.
Well, and simultaneously, the ground drops out from under the building, causing EV to reduce the gravity dead load that was keeping the building anchored heavy and flat.
The building is at its absolute most vulnerable point to tipping over. The ASCE 722 load combinations force engineers to calculate exactly that. You must combine the maximum horizontal push with the worst possible upward or downward vertical jump to ensure the building remains rooted in reality.
It is an unbelievable, highly orchestrated process.
We have taken an incredible journey today. We started with a raw, theoretical ground acceleration recorded by the USGS on bedrock.
We mathematically adjusted that wave for the jelly-like amplification of soft clay soils.
We factored in the critical human stakes through risk categories. We took a deliberate, calculated 33% reduction to balance societal economics with human survival.
We leveraged the physical yielding and ductility of secret weapons like the steel EBF link to absorb energy.
And finally, we mathematically distributed that inertial force up the height of the building like a whipping broom to ensure the foundation doesn't slide, crush, or tip over.
It is a deeply refined language of survival that represents decades of learning from past tragedies. Every variable in ASCE 722 is practically written in the rubble of buildings that didn't have those equations.
I want to leave you, the listener, with a new paradigm to ponder as you look at the buildings around you. We spent this entire deep dive exploring ASCE 722's foundational philosophy. The goal is to prevent building collapse and save lives, even if the building is completely destroyed in the process.
Right.
But right now, the structural engineering industry is locked in a massive, monumental debate. What if we designed buildings not just to survive as a total economic loss, but to be immediately reoccupiable the day after a massive earthquake?
Functional recovery.
Exactly. How would these system factors, our reduction, our omega overstrength, our CD deflection, how would they all need to change if our goal wasn't just bare survival, but total functional recovery? What happens to the math when the blueprint is expected to hold true even after the Earth moves?
It would rewrite the entire code book.
That is something to keep an eye on. Thank you for joining us on this deep dive. See you next time.